BYU Physics. I'm Mr. McConley, and today we're going to talk about what happens to waves when they change materials. And first I'm just going to start with a little bit of a discussion here. When the air changes temperature, the speed of sound also changes. And in fact, at 0 degrees, the speed of sound, the velocity of sound, we've already mentioned, is 331 meters per second. That's at 0 degrees Celsius. But as that temperature rises, actually each degree that you go up, so if you increase 1 degree Celsius, you will actually also increase the speed of sound by 0.6 meters per second. So every degree you go up, the speed of sound actually travels a little bit quicker. So you can see that since you've changed something about the material, you will actually change the speed that that wave travels. Now, that's for a sound wave. Other material waves, like a slinky, if you send a wave down a slinky, there's a certain speed that it will travel, and I don't really know that off the top of my head. But there's a certain speed that a wave can travel in a slinky. But if you take the same metal material and you coil it tighter and make it what we call in physics a snaky, so this is a snaky, it's the same metal material but it's coiled in a different way, then the speed of the wave will actually change considerably. And the wave will actually travel faster in this snaky material than it will in the slinky material. And it's the same material though, it's just the way you coiled it. Another example would be, they never stay where you want. The other example would be if you're talking about water. Water, if the depth of the water changes, it actually affects the wave travel. Okay? So those are just some examples to get your mind warmed up. But what I really want to talk about is jumping off of our demonstration that we did the other day, where we had a student yell in the back room, and you could hear him, and you notice that the amplitude got smaller, so we established that when sound travels through a solid wall, the amplitude, the noise level, the loudness got less. But I want to talk about what happened to the other characteristics of a wave. And what we're going to focus on here is that velocity is frequency times wavelength. Velocity is frequency times wavelength. So what we established the other day was that the student's voice had the same pitch. His pitch did not change. And we said pitch is the same in physics as saying frequency. So when you change materials, when you go from one material, one medium to another, like his voice went from the air and then it hit the block wall, so it changed material, and then it went back into the air, we could hear it. But anyway, the frequency, the pitch, remained the same. And in fact, what's true about all of the examples that we're going to talk about here is that the frequency of the wave will not change. That's kind of a universal principle here in physics. When you change material with a wave, the frequency will not change. And if the frequency doesn't change, what other thing has to remain the same also? What's the one that's directly tied to frequency? And it was tied by this equation, period. So if the frequency doesn't change, the period isn't going to change either. Okay? That's an important concept to keep in your mind. So frequency remains the same. But let's look at a specific example. If we're talking about the material wave sound, and we're going to take sound and there's going to be a sound that's made in the air, and then that sound is going to be allowed to travel into the water, what will happen? Well, when the sound goes into the water, the velocity of the sound will increase. Sound actually travels faster in water. And if the velocity increased, then the wavelength, how long the wave is, has to increase also, because this equation has to remain true. So if this goes up, that has to go up also. And you can think about this in your mind, because if you've gone swimming in a large body of water and you've gone underwater, you might hear sounds very clearly. Like you might hear, I've personally heard motorboats, like I hear a motorboat engine, I pop my head up and I look, and way off in the distance is the motorboat, and I can't even hear the motorboat in the air. The sound's not even making it to me, but underwater, I can hear it clearly. That's because underwater, the velocity, the wavelength increase, the sound actually travels better underwater than it does above. Another example, material wave. If you have a transverse slinky wave, and we're going to send a wave down, a transverse wave down the slinky, and we're going to attach it, we're going to attach the slinky to the snaky. When the wave reaches the snaky is more rigid. What's going to happen? Well, when you reach the snaky, the velocity is going to increase, and therefore the wavelength is going to increase. So generally speaking, what we notice here is in material waves, when you hit a more rigid material, the part that continues on, it usually increases in wavelength, it increases in speed. That's not really true when you talk about electromagnetic waves. Those are the other type of waves. Electromagnetic waves, one example being light. If we think about light and it's traveling through the air, and then we send light into glass. So we got like the light's going to go through a window of your car or a window of your house. So when the light hits the glass, what happens to its speed? Well, it actually slows, or it decreases. And if you decrease the speed, then the wavelength must also decrease or become shorter. So when light enters glass, it actually slows down. So what can we say here? When electromagnetic waves enter more rigid materials, because glass is more rigid than air, when electromagnetic waves enter more rigid materials, they actually slow down. When material waves enter more rigid materials, they actually speed up. So you can see that the waves definitely perform differently. Now, the last thing I want to wrap up with here is just to remember the whole picture. When a wave is traveling along, or a single vibratory disturbance is traveling along, and it meets up with a different material, this is a different material here, part of the wave is always reflected, and part of the wave is always transmitted. And today what we've talked about is the part that gets transmitted, what happens to it. The other day when we were drawing the pictures of the waves bouncing off, and some of them were inverted and some of them remained on the top, we were focusing on the reflected part. Today our focus is on the transmitted part, and we've learned that electromagnetic and material waves perform differently. For today, physics.